All right, starting with bonding and molecular structure. Your notes start with, what is a chemical bond? Okay, we're going to be talking about that. They are the attractive force that holds a group of atoms together and makes them function as a unit. For instance, water is a bond. Individually, hydrogen and oxygen act completely different than H2O. Okay, the bond also is talking about their physical properties, such as melting point, and their solubility characteristics. When we're bonding, the reason we bond is that nature, or the system, is trying to achieve the lowest possible energy state by bonding. Okay, energy is released when a bond is formed. We talked about that in thermochem, and of course it requires energy to break a bond. Also in thermochem, we defined the bond energy as the energy required to break the bond. Okay, when we're talking about bonding, and we're going to split this up kind of into two parts. This unit is pretty much just going to be about intra-bonding, which is the bonding between atoms that make a molecule or make a bond. The inter-bonds we'll talk about in the next unit when we do states of matter, solids, liquids, and solutions, because we've already done the gas units. We'll revisit a little bit, but that is like the interactions of why one has a higher melting point than the other. That's going to be the next unit. Okay, this unit is pretty much going to be Lewis structures. You're going to have to draw the crap out of Lewis structures. Okay, and molecular geometry and polarity and how those things affect that. Okay, so two things that you want to look at is the interbonding. Both are based on Coulombic attractions, but one is weaker or stronger. Obviously, intra is the bonds that hold the atom together. They're going to be a stronger bond. Okay, and here's a handy dandy little chart. Okay, that kind of takes you through that process. So this side of the chart is pretty much next unit. A little bit may come up. You should be familiar with overall from Chem 1, the intermolecular forces. Sometimes you'll see them called interparticle, but you don't have to go into them to great detail. That's for the next unit. But you should be aware of them, okay? And we're going to primarily be talking about ionic and covalent more so than metallic, although you do have to know the qualities and properties that metallic bonds have, but there's not a whole lot of exciting things going on in terms of talking about it. We'll really spend the most time on covalent because most of the world is a covalence. Okay? All right. The two types of bond, or three types of bonds are listed here. Just an overview. Ionic, of course, is the electrostatic attraction between ions, right? What two types of ions? Cations and anions, yeah, positive and negative. And they're usually produced between a reaction of a metal and a nonmetal. They have very high melting points. Normally they are a solid at room temperature, and the attraction is very, very strong because the ions are very close together in a crystal formation. Covalents are when we're sharing. Sharing is caring. Don't be ionic, be covalent. And of course, then we're going to talk about that later. It's not usually 50-50, okay? I just threw Coulomb's law in here because it's important. Okay, so there it is again. You're going to see it a lot. And then metallic bonds, remember, is basically it's the socialism of bonds. The electrons belong to everybody and they all share them. Okay, but that's your delocalized sea of electrons where the electrons basically belong to all of the positive nucleuses. Covalent bonds, your electrons are being shared, and they do so that everybody's trying to get to an octet. And so if they are able to achieve that full outer S&P sublevels, it decreases their potential energy. So when they do that, these actually will form what we call molecules because they are attached. Their orbitals overlap and they share that electron between the two atoms, and so they are forming a molecule. Okay. If we're sharing one pair of electrons, we have a single bond. If we're sharing two pair, we have a double, and if we're sharing three pair, we have a triple. Okay, and then of course these are usually between two nonmetals. Okay, when we're talking about any kind, we're looking at the atom being attracted to the electrons on the nearby atom, and it makes it more stable. And of course, it's trying to lower the energy. I gave you lots of words in there you can read. I'm going to do an overview of this part because hopefully you remember what these bonds are from Chem 1. Okay. All right, so what does that look like? Here's a graph. Okay, you have two atoms, and as they approach each other, if they get too close, they repel. But if they get just the right, like the Goldilocks state, then they bond. And they do so at where it's going to be the lowest potential energy, and then that would also give us our bond length. So that length of bond is where it's the minimum amount of potential energy. Okay. Otherwise, then they start getting too close, and then they, like two magnets of positive ends, they start repelling. So it's they have to be at the don't say the Goldilocks state on AP tests. Okay. Bond properties. We're going to talk about bond order a little bit later in the notes, but just for right now, simply put, a single bond is bond order of 1, a double is bond order of 2, and a triple is bond order of 3. Okay. And then bond length, of course, is that distance of the two bonded atoms at which the potential energy is minimized. And then depending on the single, double, triple, the bond length is the shortest in a triple, which makes sense because it's getting those nucleuses even closer together. And of course, the strength is also strongest for a triple bond. Bond energy, greater number of electron pairs. That makes sense. This all makes sense. We know this already, right? Triple bond's going to have a higher bond energy. And the bond dissociation energy is the energy supplied to break a chemical bond. Bond energy for short. And there's an example of hydrogen. Okay? So this means this would require, this much energy would be required to break the H2 bond. So we expect that to be endo or exothermic. It's positive. Endothermic. Positive is endothermic. We're having to put energy into the system to break that bond. Okay? So that brings us to electronegativity and dipoles. Remember, electronegativity is the ability to attract an electron to itself in a compound, different from electron affinity. Electronegativity says, hey, we're both wanting this electron, who gets it more? It's like a tug of war. Okay? Fluorine, of course, is the most electronegative. Everything else is assigned a value relative to fluorine. Fluorine's a 4. Everything else is relative to fluorine. Okay? And so if the elements have very similar electronegativities, they will share it equally. And we call that a nonpolar covalent bond. So you might want to, did I highlight it in your notes? Did I bold it? If I didn't bold it, you should underline it. Nonpolar covalent is equal sharing. Okay? And so that would be an example of that. They're sharing equally. Okay? If they're not sharing equally, it's a polar covalent bond. So they have greater electronegativity differences, it becomes a polar bond. If it's a high enough electronegativity difference, we call it an ionic bond. Okay? These presence of these dipoles and the intermolecular Coulombic attraction determines the type of intermolecular force that's going to be present, and also will greatly influence their properties, which is going to be the next unit. I'm just leading you up for that next time. So if something is a polar molecule, it's going to behave differently with its intermolecular forces than something that's nonpolar. Okay. Here is a chart of electronegativity differences, so you can kind of see. I will tell you that this cutoff right here, actually all of these, can be different depending on what chart you look at. Okay. Some charts say that nonpolar is 0.3 or less. Some say 0.4. Some even say 0.5 or less. Okay. Just depends on who decided to say that chart. Same thing with ionic. Some do 1.7. Some go as high as 2.0, as the difference has to be ionic. The point of all of this is most things are not purely ionic or purely covalent. Some of them can have more ionic character. Some of them can have more nonpolar character. There are a few things that are purely one or the other. What is something that is purely nonpolar, though? Oh, I'm going to let you retract that. What is something that's purely nonpolar?
Oh, that would be like hydrogen gas, chlorine gas.
The diatomics. If something's bonded to itself, the Brinkelhoffs, then they have a 0 electronegativity difference. So they are truly 100% nonpolar. I'm going to ignore that you said that word back there. No, because most things are, if they're polar, they're going to have a percentage of ionic character to them, and most things that are ionic have a percentage of polar character to them as well. Well, I mean, if you,
Like, are we?
no, but if you're looking at this scale, like if you notice the arrow, it says covalent character decreases as ionic character increases. So, like, 1.7 is usually like the cutoff to say, okay, now we're going to say it's ionic instead of, but if you're sitting at 1.5, it's going to have some ionic character to it, even though it's going to fall under the polar block. Does that make sense? Oh, you have a question?
Yeah, so what does that look like on the AP test? Do they give you the values of certain
If they
elements?
want you to calculate that, they'll give you the values. They don't expect you to memorize any electronegativity values. They do expect you to know that fluorine is the most electronegative.
Yeah.
Okay, they do expect you to know that. So here we have this Pauling scale, and here's hey, that's like we planned that question because we're going to do that right here. I'm giving you the electronegativity values of those, and we're going to order the bonds according to the polarity. So we're going to start with the most nonpolar and go up to the most ionic or most covalent. Okay, so I want to do what? Some simple subtraction problems, right? So HH is going to be an EN difference of what? 0. Okay, so that's a 0. The OH difference is,
Oh, wait, never mind. 1.4.
1.4. I'm just going to list them above. The HCl difference is going to be 0.9. And then the SH. And then the FH. So we would just simply list those. We'd say this is the least. So that's less polar than SH. Less polar than CLH, less polar than OH, and then this would be the, so this is the least, because it's actually nonpolar, and this would be the most. Now, a greater difference of 1.9 would say that that's an ionic bond, but in fact it's going to be more covalent. I mean, it's going to have a lot of ionic characteristics, and but it will be, because it's between two nonmetals, we would still probably call that a polar. Okay, we would also find that that's such a strong bond that when if you put it in water, it's an acid, but it has very little dissociation. It's considered to be a weak acid when it's dissolved in water. Whereas where HCl is not in the middle, when we dissolve that, it's a strong acid because it's 100% dissociation, and that's a lot of it has to do with their bond characteristics. We're good so far? This is stuff you should remember. Ionic bonding, of course, is the outright transfer of the electrons, giving and taking. When the electrons are completely transferred, the electron cloud distribution looks like this. They're separate. They're not connected. And notice what happened to lithium. Lithium atom, what happened to it went to the cation. They got smaller. And what happened to fluorine? They got bigger. Okay. So if we were to draw that in a particular or particulate diagram, make sure you draw the cations smaller than the anions. Here's another. Why do they transfer their electrons? Because they're trying to achieve that octet in their outer level. And so if they give or take, they can get to that point. So the metals give away typically, not typically, the metals give away. And then the nonmetals can either take or they can share. They're very versatile. Just reminding you, metals tend to lose their electrons and form cations. Nonmetals tend to gain and form negatively charged anions. And then Coulomb's law is very much a factor for ionic compounds. It says it on your notes, but it doesn't have this pretty picture for you that I found when I was making the PowerPoint. Because of that, what Coulomb's law says, we want to look at charge and size to determine which is going to have a higher electrostatic or Coulombic attraction. So the things that are very small atoms or the things that are highly charged are going to be your stronger bonds. And we're going, I say we, one of the days that I'm gone, you're going to do a POGL on lattice energy and Coulombic attraction that will help walk you through that. But in a nutshell, Larger charge or smaller size is going to affect the Coulombic attraction. So, with that in mind, let's look at this first one. Which of these two would expect to have a stronger bond, NaCl or NaBr?
Actually, the NaCl is going to be smaller.
Right, NaCl, because the Cl is smaller. So your distance, now this time when we're talking about distance, when we're talking about atomic structure, we're talking about the distance between the electron and the nucleus. We are not talking about that distance now. What distance are we talking about? Between the two ions. How close can they get to each other, right? So chlorine is smaller, so it can get closer to sodium. Bromine's bigger, it can't get as close. Their nucleus is to their valence electrons. Okay, so now when we're talking distance, we're not talking about nucleus to electron of the same atom. We're talking about this atom to this atom, which can get closer. Okay, and then between the second two, which would be some higher or stronger bond, NaCl or MgO?
MgO.
And why?
Suppose.
Say what? I can't hear you. But if you look at them, it's going to be something different here. Charge.
Yeah, you'd be more charged.
They have higher charges, so now that numerator number is going to be bigger. Yeah. Okay? So those are the two things we're going to be looking at. When we're talking about ionic compounds, of course, they are in a, usually they're solid, and they are in a fixed, rigid position, and they're in a three-dimensional lattice or crystal structure, okay? That means they're not malleable, because if I start banging on an ionic solid, it shatters because of the way that they're held together, the planes break apart, okay? So it kind of looks like this. They are very structured, alternating positive negatives. So if you notice, each one of those negatives is only surrounded by positives, and vice versa. Each one of the positive ions only surrounded by negative, okay? Again, draw your cations smaller, okay? These strong bonds are why ionic solids have a very high melting point, very high boiling points, and they will only conduct electric current when they're dissolved in water, because then the ions break apart, so they're swimming around individually, or when they're melted or molten, because what happens when I melt it? What can the ions do? They can move around because it's melted now. It's a liquid. Yeah, it can move around. Okay. Okay, that brings us to covalent bonding. We're going to draw Lewis structures today, but we're going to stop short of the shapes. We'll do the shapes tomorrow. Do y'all remember that from Chem 1? Tetrahedral, trigonal planar, trigonal pyramidal. Yeah. Yeah. Yeah, if you didn't like it in Chem 1, you're definitely not going to like it in here. Okay?
Good thing I loved it in Chem 1.
I'm glad you loved it. All right. All right, so there's going to be a couple of different models that we'll look at. The localized electron or bonding model is assuming that we are sharing pairs of electrons using their atomic orbitals. And the electron pairs are assumed to be localized on a particular item. So we have lone pairs or in the space where we're bonding shared pairs. Okay. The Lewis structure is going to describe that arrangement. We're going to do the geometry with Vesper. Remember Vesper? Probably not. It's the thing that tells us what the shapes are. And then the description of the orbitals are blended. Okay, so we're going to get through all that. How do we draw this? A couple of things we need to remember. First, the octet rule predicts the number of bonds based on the number of unpaired electrons in a Lewis structure. We use a dash to represent a bond, although you can use two dots. And then for unshared pairs, we do the lone pairs as a set of dots. Remember that? Okay, single bond, one pair of electron. Multiple bonds often formed. Here's how you can remember what forms multiple bonds. Synops. Okay, and a matter of fact, they are in order because carbon and nitrogen can form single, double, or triple. Oxygen, phosphorus, and sulfur will form double. On rare occasions, oxygen can triple bond, like in carbon monoxide. And then right now it's talking about sigma and pi bonds. Don't worry about it for now. That's for later on when you go back and study and you know all this. We're going to talk about sigma and pi bonds later. A single bond is always a sigma bond, so those are always present no matter what. And then pi bonds are multiple, and so they show up when you have a multiple bonds. But we'll get into that later. Okay. Exceptions to the octet rule, fewer than 8. Of course, hydrogen can only have 2. Pretty much anything from boron below can't get 8. Boron will get 6, and then we drop back down to getting 2. For instance, beryllium has 2 valence electrons that it can share, because it's weird, or give away. And so it can't ever have 8, because if it gives it away, it's going to have 2 in the lower 1s2 level. Anything in the 3rd period or greater can expand its octet. So sulfur and phosphorus really like to do that. They can get more than 8 around them because they have some d orbitals available to them. Even though the 3d doesn't show up until the 4th period, it's still part of the 3rd energy level, right? So they can expand and utilize those empty d orbitals in that energy level. And then a few weird oddballs can actually have an odd number of valence electrons, and so they don't obey the octet rule either. But we assume, unless we know it's an exception, that it obeys the octet rule. Lewis structures, you can read through that. Here's the rules. Okay, rule number 1, calculate the number of valence electrons, taking into account any charges that are present. Okay, so if I have a negative, what am I going to do with electrons? Add some or take away? Add. So if I'm doing a polyatomic ion, like a phosphate with 3-, I would figure out my valence electrons for my elements, and then I would add 3 to that because it's got a negative 3 charge. Decide which one is the central atom. If it's not obvious, it's going to be the least electronegative, with the exception of hydrogen. Hydrogen will never be your central atom. Why? Because it only has 1 valence electron to share. Yeah, and it can't get, it's in the 1st energy level, so all it can fill up is its 1s. So it's only going to form 1 bond. So hydrogen will always be your terminal atom, okay? If you have carbon present, carbon's going to usually be your central atom, okay? And generally, when you see a formula, generally, unless it's hydrogen, whatever's listed first is generally your central atom, but not always, because of organic compounds, okay? So then we're going to use 1 pair of electrons to form covalent bonds. So give everybody 1 bond to attach it to start with. We call it the skeleton structure, okay? Then you're going to place lone pairs around the terminal atom, except for hydrogen, to make sure they satisfy the octet rule. And then any leftover pairs we're going to assign to the central atom. If the central atom is 3rd period above, we can expand. And if we look at the central atom and it's not yet surrounded by 4 pairs or an octet, we're going to convert 1 or more of those terminal atoms into a multiple bond. Okay? And of course there's some that will be electron deficient. So, with that being said, let's draw some structures. Yay. If you don't, I think I did leave y'all lots of room, didn't I? Yes. Okay, we'll start with the easy one, CH4. How many total valence electrons are going to be present in this structure? 8. Why? Because carbon has 4, hydrogen has 1, and there's 4 of them, so 8 electrons. Okay, so I'm going to draw my central atom, which is going to be carbon, and I'm going to attach all 4 hydrogens. Each line represents how many electrons? 2. So I have 8 electrons, so I'm done. That's the easy one. Okay? Let's do F2, also easy. I'm going to change colors. How many valence electrons do we need? How many valence electrons does 1 fluorine have? 7. So how many should 2 fluorine have? Okay. Okay. Thank you, D. Beck, for the win. All right, so now I've drew them and connected them, so now I give everybody their lone pairs. Hold on, I'm going to do this. Red. Well, just hold your horses there, kiddo. I'm building you up. Okay, so also finish now. Right? Let's see. I'm going to do. I should not have done that. No, I was thinking I should have just used red and orange for asteroids, but I didn't. Okay, so now we'll do O2. Oops. That's a fat O. That O had too many cookies. Okay, so O2. Let's try this again. How many valence electrons? Come on, we can do it. 12 valence electrons. Okie dokie. So oxygen, right? It is going to be double bond. Do you remember that, or you just know, or how do you know?
No, I was because it's one of the ones that help.
What's your logic, Josh?
Right? But I will show you this to help you know how that seems logical. That's what an oxygen looks like. It has 6 valence electrons. Remember electron dots? So it needs 2 bonds. Okay? So it's going to double bond. And then we're going to put the electrons. And when we draw the electrons, we draw them as far apart as possible. So it looks like that. And then comes nitrogen. How many valence electrons? 10. Okay. Well, nitrogen looks like this when you draw its electron dot. So how many bonds does it need? 3, wherever there's an open spot. So there's nitrogen. Okay. You feel like that'd be what? A logo. It could be. Yeah, it could be. Okay. Does everybody have these? Because I'm going to erase and draw some more structures.
No, I'm not. I don't.
Oh, I thought he was telling me no. Okay, after that we have HCl. Oh, well, I forgot to change. We're going to... Hey, don't body shame the HCl. Okay.
It has 8.
It has 8 electrons.
Oh my goodness.
So it's
We're going to give them, we have to give them fat dots too. We can't give him skinny dots. That doesn't go with his body style. Okay. My HCl is sad because y'all made fun of it. Okay, and then HF is going to, I'm not going to do HF because it's going to look just like HCl, but just substitute the F. Okay, so let's go on to another one. How about water? H2O. How many valence electrons do I need for H2O? 8. Okay, so I'm going to draw an oxygen, and I'm going to add a hydrogen, and I'm going to add a hydrogen. I only have 4 electrons. Oxygen does not have an octet, so what do I need to add? 4 more, yeah. So we're gonna do, now you would probably normally draw them like this. We will find out tomorrow that's not what it looks like.
Yeah, it's.
Oh, I did it.
it's bit. Do we have to bring out some protractors, or is it 100?
Only you do, because, yeah. So make sure you bring that to the test. Okay, so ultimately we'll find out that when we have 2 lone pairs, it looks like this, and it's bent, but we'll save that for tomorrow. Okay, how about the wonderful, lovely NH3?
Is it just like
It's also 8.
Is it just like
How many valence electrons does nitrogen have? 5. So it's going to look like this. We're going to draw our nitrogen, and we're going to attach our hydrogen. And there you have it.
They all go down.
Yeah, we're doing structures, shapes tomorrow. I want you to draw the little structures now, shapes tomorrow. Unless you want me to go through the shapes and I'll give you the work for tomorrow today. Yeah.
We're just getting.
We're just getting a feel for it. You are right.
I'm trying to remember if I remember.
Okay, so we're on CBr4. CBr4. Carbon tetrabromide. How many total electrons do I need?
32.
Ooh, good job, 32. You need 7 times 4 is 28 plus the 4 for carbon. So we're going to draw, we're going to attach all of our bromines. And then we're going to go give all of our bromines their octet. So give everybody 3 sets of lone pairs or 6 valence electrons. And hopefully you should add that up. And it should add to 32. Do yourself a favor, when you're counting electrons, count by 2s. My pre-AP kids are going 1, 2, 3, 4. I'm like, count by 2s. It's twice as fast. Yeah. Because the bonds are 2, the dots are 2, count by 2s. Okay? And then let's go with a PF5. PF5. What? 40. Should have 40 valence electrons. Right? Because 5 times 7 is 35, and phosphorus is 5. So there we go. So, where is P located? Filter. Okay, so what group is phosphorus located in?
15.
Except I asked the wrong question. What period is phosphorus located in? 3. And what did we say about
It can expand. Yeah.
period 3 or above? It can expand, which is why it has 5 things. So we want to spread those out as evenly as possible. Put the F's on there and give everybody their lone pairs. And if we do that, just like magic, it comes out to 40. Okay? There's 2 more left on there, but we are going to run out of time. But I do want to address the last 2, just real quick, not drawing them, but like electron-wise, because there's charges. So we have P. That's not going to work. So we have PCl6 minus and NH4 plus. So tell me how many electrons each one of those should have, just so you know that when they're negative and positive, what you do.
48.
48 for this one, because we had to add 1 because of this. And then NH4 plus. 8. Because we had to subtract 1 off for that one. Okay, so draw those just real quick on your own and I'll check them out. Okay.